Hi everyone. Starting a bit late, so I'll get cracking. Thanks for coming along. I can promise you no terminal windows and a larger font, so hopefully you'll be able to read what's going on here. A slightly different tack, a little bit more on I guess motivation for the sorts of technologies that XMOS are developing, particularly the motivation behind developing RISC-V architectures that are targeted towards empowering embedded software engineers to create their own system-on-chip solutions. Before I start getting into that, just very quickly on XMOS, as you may have gathered, XMOS is from the UK, based around Bristol. We've talked about software-defined system-on-chip technology. That's the sort of value proposition of the company. We're on our third generation in volume of multi-core microcontrollers, and I'll talk about the motivation for that in a moment. We have 500 customers annually, thousands of users, tens of millions of chips in the market, over hundreds of applications in consumer, industrial, and automotive markets. So we've got a bit of a pedigree for building processor architectures. The reason why we're here this week is because of our latest generation. Our fourth generation is RISC-V compatible. In terms of motivation, the recognition of the founders of XMOS was that the drivers of the semiconductor industry were changing. This was 15 years ago, and I think over the last 5 years, this has become something that's widely recognized. We're moving from a low-mix, high-volume markets into something we're calling the IoT, which we tend to bandy around as though it is a market in its own right. It's actually a sum of niche markets, each one of which is sort of small or medium-sized compared to some of these previous drivers, with its own requirements, with its own diversity, significant fragmentation, and very dynamic evolution. So targeting something like the IoT with the techniques that we use to create solutions for these previous markets, our contention is that that's not the optimal approach, and it may even be quite broken. The reason why we say that is because the cost and the time to market primarily. So this graph is from DARPA. It costs $50 to $100 million to develop an SoC, a system on chip, using traditional methods. It takes at least 2 years. I'm sure many of you would have been involved in projects that take significantly longer. And it's very difficult to hit a market that's big enough in the IoT that can tolerate that level of time to market, can tolerate that 2-year time to market. So what we're seeing amongst product planners for these traditional approaches is they're either not really getting started, they're sort of atrophied, or they are designing chips that are a superset of the needs of any given market. So they're throwing the kitchen sink at a system-on-chip device. So not only are they tolerating the long time to market, the very high development costs, but they're also compromising their variable costs. They're compromising the cost of the silicon itself. And we'll talk about hardware scalability in a moment. But what we need to do is to try and solve for those problems. And this is an area that XMOS set out 15 years ago to solve, even before the IoT wasn't really called the IoT. I can say with my hand on my heart that right from the very beginning in XMOS's history, our mission was to deliver the most adaptable, efficient, and accessible computing platforms for the IoT, or what's become known as the IoT. This is the second time we've used I've seen a Darwin quote. This one's slightly modified, but it's our contention that it's companies that have that kind of agility, that kind of agile technology that will really succeed in the market. So let's start peeling the onion on what it is, what XCore is. All of our generations of devices are called XCore. As I say, we're on our third generation in volume. One of the ways of describing it is it's flexible like an FPGA. It's not an FPGA, and we'll talk about the architecture in just a moment, but it exhibits that kind of level of flexibility right to the edges of the chip. It's high performance like an application processor. If you look at our portfolio of products, they can be clocked at 500 to 800 megahertz. So very high performance for the class of solution that we're delivering. And it's scalable. It's actually got built-in scalability. So this is a perspective, if you like, on flexibility. If you run out of performance in one chip, you can put another chip next to it. You get a linear scaling of performance and the same programming model. So it looks like a single chip with twice the resources. So that's another dimension on flexibility, if you like. The closest thing to describe what we do is microcontroller. That describes the space that we're in. And that comes with some hygiene factors like ease of use, affordability, and low energy. So, of course, we have to deliver on those expectations as well. And whilst we've targeted ourselves commercially at consumer and commercial environments, consumer and commercial applications, our customers have picked up this platform, recognizing its intrinsic value, and pulled it into every market pillar of the IoT, so automotive, transport and logistics, and industrial. In terms of portfolio, so we're on our third generation in volume, so that's the one in the middle there, which came to life in 2020. As we've gone through these generations, our motivation has been to be the only processor in the box. So originally, back in the early days of the business, we wanted to marry the processing performance of something like an MCU with the I/O flexibility of an FPGA. And that enabled us to win in audio bridging. This was around the time when Apple stopped using FireWire on MacBooks and wanted the industry to adopt USB audio too. There was no chipset except XMOS. We had a flexible platform. We developed an SoC solution to that using the software methodology that's intrinsic to all of our technologies. Got to market first, obviously, and we've won the market, and we've been very dominant ever since. We're always looking on the board, though, when we see a customer's design, we're always looking for the next thing. What's the next class of processing that we can bring into the device to increase the level of integration, increase the value? In an audio context, that was DSP, so our second generation was designed to accelerate DSP. Our third generation was designed to accelerate AI and DSP as well. Now, our fourth generation, which hasn't quite got into the world just yet, is doubling down on many of those features with architectural improvements, but critically is now going to be delivered through a RISC-V compatible framework. So that's why we're here. I'm very excited to announce the fourth generation, which will be with us in the second half of next year. In terms of what you can do with a device that is capable of delivering hardware-like behavior alongside all of the other classes of processing, there's two real ways to benefit. The one is integration, and the other is differentiation. And of course, you can do both at the same time. This is a great example of a customer that's taken the classes of competitor that we typically face, microcontrollers, DSPs, FPGAs, and demonstrated that you can just create a single solution using one XMOS device that beats all of those classes of competitors in one hit. So this is before on the left-hand side and after on the right-hand side. So it's a very strong, a very powerful message that's been repeated many times that demonstrates how versatile and capable the XCore processor is. This was done to get to market fast. This bomb saving, I can tell you, was over 70%, but this particular customer was interested in getting into the market quickly. Now, we're a processor company. We're a fabless semiconductor company, so we make our money from selling chips, but of course, in the modern world, you can't just sell chips. You have to provide software, obviously, tools, and so on. So we build a lot of capabilities on top of those chips that create building blocks for our customers and partners to build systems. So we're particularly well adapted to AI at the edge, so edge processing for imaging, voice, audio, and even radar. So we build those libraries, we deliver those libraries alongside our tools, and our customers can piece together systems on their own. We have a particular emphasis towards the left commercially here, but it's interesting to note the little green blobs are where our systems are being shipped in volume. So you can see that we're already present in some of these other areas of the IoT and delivering in volume, despite effectively not pushing the technology in that direction. So I talked about, at the very beginning, I talked about XCore and I talked about a multi-core MCU. So let's unpeel the onion a little bit on the architecture. There's a little bit of a hint at the bottom there. But let's just talk about the motivation of a multi-core MCU. It's perhaps slightly different from a traditional motivation. The reason why we are building multi-core MCUs is because we know we need to marry hard real-time and soft real-time together on the same platform. Now, what's hard real-time? Hard real-time is a system where failures to meet deadlines cause catastrophic failures in the system. Soft real-time, by contrast, is where failures cause gradual degradation of the system. Now, it's perhaps a slightly different way of looking at things, but my contention is that every embedded system in fact, every system has hard real-time. It's typically embodied in hardware because we don't trust software, we don't trust the platforms that software run on to deliver at hardware levels of determinism and granularity. So we've always got hard real-time. We've sometimes, perhaps most of the time, got soft real-time, and we have to manage those two things alongside each other. Hard real-time tends to be delivered with spatial partitioning, so you reserve areas of silicon for delivering that kind of that function. Soft real-time typically gets delivered by an operating system. So it's perhaps not too much of a surprise. I won't go into too much detail on the architecture, but certainly I would invite you to come and talk to us if you want to know more. It's perhaps not too much of a surprise to see that there's an array of resources, that can be dedicated either to this spatial allocation or to the time-sliced, more temporal allocation. Each one of these white stripes you can see is a RISC-V heart in the 4th generation. So each one of those devices, each one of those hardware threads is capable of any one of those classes of processing: control, DSP, AI, or I/O processing. So they can be statically allocated to tasks like that, or they can be dynamically allocated to fulfilling those functions. And you can see there's a replicated module here. There is what we would call 2 tiles. And in between those 2 tiles, there's a switch. That switch enables those hardware threads to talk to each other on the same die, on the same tile, but also it enables those hearts to talk to other hearts on different die or in larger systems. So that's where the scalability, the built-in scalability comes from. And this hard real-time requirement that we have in order to complete the picture, in order to be able to complete the building of systems on chip devices in software, is pervasive in this architecture. If we were to look deeper and deeper, you would see more and more features that either have been included or excluded because what we need in order to generate hardware behavior in software is single-digit nanosecond resolution and absolutely bulletproof hard real-time behavior. So when you look at how you put systems together, this is an XCore in the middle, as you probably now recognize. We have a combination of things in systems. Typically, we have hearts that I've called them here bare metal. These are the parts of the system that absolutely must meet hard real-time deadlines. And they will have some sort of a spatial allocation, so they will have a number of hearts dedicated to the delivery of those features. And then in the purple box, there is a temporally multiplexed compute resource where we've taken some of the other hearts, some of the spare hearts, if you will, and we've put them together under the supervision of an operating system. So the bit in the red box, if you like, you might normally expect to find in hardware. The bit in the purple, you might normally expect to find that in a processor. But the key thing here is that this has all been delivered using software on a pre-existing hardware platform, so significantly cheaper and faster time to market. So the next few slides cover a few real examples. So this is an example of a voice processing system. So on the left-hand side is, my best approximation of a software way of looking at the world. You can see an abstraction, FreeRTOS abstraction with application tasks on top of it. So that represents the softer real-time elements. And then beneath the FreeRTOS line, there's those device, what you might normally expect to be as device drivers. In this case, the device driver actually contains the behavior of the underlying hard real-time tasks as well. So on the right-hand side, you can see how those I/O protocols, those DSP pipelines, those AI models that require that hard real-time behavior have been mapped onto their own hardware threads. And then there's this shared resource, FreeRTOS, which is striping application tasks across, in this case, three hardware threads. So that's a voice interface. Moving to something a little bit different, same silicon. This is a number plate recognition system. Again, a real example. This one's on the metal, so this one's only using those hard real-time facilities. You can see an image pipeline on the right-hand side and a number of hardware interfaces implemented in software on the left-hand side. And that's a mass-market automatic license plate recognition system, which will be shipping in volume next year. Last but not least, again, same silicon. This is a multi-axis motor controller. So this is a robotics controller. Not only is it controlling the motors on the right-hand side, it's also controlling the trajectory on the left-hand side with an operating system and some tasks striped across, and again, 3 hearts to control the application layer. So there's 3 different application domains, 3 different markets, same silicon, just modified with software. And those are a little abstract. These are very real. So there's, as you can see, I talked about robotics down in the bottom left-hand corner. We do a lot of work in voice, a lot of work in audio processing. If you play a musical instrument, particularly an electric one, if you like high fidelity audio, you've probably got XMOS devices in your home. You can see here some of the diversity. We've got e-bikes, multi-axis motor control, human presence detection using radar and smart street lamps, all the way up to voice control, conferencing, and smart speakers, and many things in between. And this is all the same silicon, once again, modified using software. So, told you a little bit about XMOS, a little bit about XCore, and the motivation and the reasons behind the multi-core aspects of it. The fact that it needs to deliver those 4 classes of compute and critically not interfering with one another, particularly not interfering with hard real time. And as I say, the reason why we're here this week is because the shift in the 4th generation is to deliver that through a RISC-V framework. So that's it. Thank you. If anyone's got any questions, I'd be happy to have them now. We are actually just about a minute before the scheduled finish, which is good going. If you want to come and visit us in our booth, though, we can talk in some more detail. Sorry, is that a question? Hang on, there's a microphone coming.
I guess you get the same question on every presentation. How does software-defined SoC compare to an FPGA, including 2 hard cores and a fabric for doing this time-sensitive stuff? Mm-hmm. Is the XMOS solution cheaper or higher performance?
So the question is, how do we compare to an FPGA?
Including a hard core.
Including a hard core?
Yes. So we have your processing power, and then you have some.
Yeah, it's a good question. And actually, there's really 3 ways of building SoCs. There's a traditional SoC, which is slow and expensive. There's FPGAs, and there's XMOS. So to your question about how we would compare with an FPGA, there's a couple of things. I think FPGA fabrics tend to be somewhat inefficient for certain classes of processing, and power consumption tends to be higher, and consequently they also, because of the area, they cost more. But the thing that I would probably really dwell on is they're hard to program. What we wanted to do was to deliver our capability to embedded software engineers through embedded software tools using techniques they already know. And the natural thing for us to do then is not to use an FPGA, not to use a hardware construct, but to use a software construct, which is a processor. So that's the reason. I mean, I think FPGAs are good for certain outcomes. I think in this case, in the embedded space, I think we've got an edge because of that enormous design community through embedded software techniques.
Okay, it's a usability thing.
Yes, yeah.
Okay. Thank you.
There's another question over there.
Okay, it's interesting. How can you deal with the synchronization overhead among hard? Because it's a hardware thread, and so there will be a lot of communication among them.
So Henk is my CTO. He's sat right behind you. He's doing a talk on that tomorrow.
Okay.
So if are you around tomorrow? Are you here tomorrow?
Yes.
So can I suggest you attend that talk, because that is what that talk is about. And my answer compared to his will be very poor. Okay. So I recommend you do that. There was another question.
So this might be overlapping, but it looked like you were sharing your ALUs and memory access.
Yeah.
So if you have your application threads shared with your real-time threads, can you ensure determinism on those real-time threads accessing the shared?
Yeah. So the answer to that is, I mean, that's a level of detail we didn't go into. But there's just, if I can answer that sort of more generally, there's a number of things that we don't do in order to preserve the real-time behavior of one of those hardware threads in the context of soft real-time threads. So we don't share resources. There is a dedicated slot to access memory. Basically, we don't share resources. We don't have shared buses. The IOs are directly mapped into the pipeline. There's no peripheral bus that might have contention on it. So it's a lot. There are a lot of things that we do somewhat differently, because at the end of the day, we have to respect that sort of single-digit nanosecond resolution with no jitter. Okay. Thanks, everyone.